Good afternoon, everybody. It's a very pleasure and honor to be here today to give a perspective about hydropower and the critical role that it has in energy transition with advances and also research perspective on hydraulic machinery side. I would like to start my talk by showing you in Europe what are the trends and the forecasts about generation capacity increase from intermittent renewable energy sources. So focus here will be on electricity generation. You can see here in the blue bars how the forecasts anticipate a 5 times increase from intermittent generation capacity and how forecasts anticipate twice electricity demand with those gray dots in 2050 in respect to 2020 values. As we already heard in a previous presentation, this means that we need to endorse flexibility and reliability of the power system. What flexibility is? We heard this word already quite a few times in the past days. Flexibility goes over a broad range of time from short terms as the sub-seconds up to long-term years. And we need to endorse this flexibility of the grid through all time scales. So by meaning sub-seconds, it means that we need to guarantee that all time long we have a balance in both frequency and voltage of the grid. By long-term, day, months, years, it means that we need to guarantee energy adequacy. That means storage. Hydropower has the beauty to actually provide flexibility along all those timescales, and is the only renewable energy sources that can provide this flexibility. What is the challenge? Hydropower has been there for decades, centuries, right? It's considered a major technology. Let's first look at how our statistics in our two countries, Switzerland and Japan. Here you have a Swiss perspective. Hydropower, we already heard, accounts for 60% of electricity production. That means in Switzerland last year, 48.3 terawatt hours of production. Yet, hydropower has to go through a concession renewal process. Those concessions in Switzerland typically 60 to 80 years. Most of hydropower plants has been commissioned in 60s, 70s. It means that in the next 20 years, we will have the end of hydraulic concessions from more or less the half of what it produces today. Modernization, so it's a key today in order to have successful motivation in investing in hydropower and getting the renewal of those concessions according to today and future standards, both for flexibility requires from the grid as well as environmental laws. What's Japan? We already heard previously, we have a 7th strategic energy plan in Japan that counts on increasing strongly solar production, passing from 10% to up to 30% more or less, and increasing also the wind. Hydropower in Japan is at 8.5%. It will be increasing to roughly 11%. Yet, with solar and wind increase, it will be extremely important to consolidate the stability and reliability of the grid. Hydropower, this 11% will have a key role in providing the stability of your power system and avoid blackouts, for instance, as we heard risks today. Those events are more and more frequent, even in Europe. You heard probably the one in Spain that was there a few months ago. What's the issues again? So I come back to the question I asked you before. What's the issue with hydropower in all this context? Hydropower was designed decades ago. We have plants that operate that since centuries. We have a power plant that still operates since the end of the 19th century. So hydropower, and then I'm digging into hydraulic machinery perspective, was designed, and so many and almost all power plants were designed to operate at the best efficiency point and a given tiny range around it. So hydropower plants are designed basically to provide peak power in a way that it's characterized by best efficiency as a sole criteria. Today we have a paradigm shift. Today we are asked to operate in many different points where efficiency is not anymore the sole criteria to decide how to operate the plant. We have many different operating criteria. We want to stretch our operating range. And hydraulic machinery is still the same, but we did not design for that. So we have flexibility requirements in operation. We have increasing climate challenges. Why climate changes is a problem here? Water, right? Hydropower deals with water. And water is going to be less available, especially water quality is going to change and is already changing. We are experiencing more and more sediments content in water, which of course is detrimental for our hydraulic machinery. And we need to guarantee its passage for sediments connectivity and environmental restorations. So we have several new operational requirements. We have an extension of operating range, which is needed. More and more start and stop. We are switching from more or less 10, 20, up to 50 start and stop per day to now 600 startup and stop per year. We have more frequent, so in general, transient operations. We need water management in order to deal with risks in water scarcity, and we are working and operating with extreme environmental operational environment. So this is an issue for hydraulic machinery and how it was designed, because we have premature aging, unsafe operations, we are escalating the OPEX cost, we experience failure, not forecasted failures, not forecasted maintenance needs, and so unavailability of hydropower. And of course, we also are facing some environmental concerns that must be addressed. So in the sector, we are facing many developments, new strategies, for instance, encompassing operation, monitoring, and maintenance. Digitalization is key. We saw that in all sectors, hydropower should not be an exception, and novel technologies, designs, and materials. So with this, I would like to introduce a few recent topics on which we have been working on at EPFL and also beyond EPFL, as hydropower, and in particular research in hydraulic machinery, is still active and must be active in order to have hydropower ready to tackle energy transition and climate change challenges. I would like to wrap up with three main categories of studies that are ongoing in hydraulic machinery worldwide. Here you can see a beautiful flow phenomenon that happens in the hydraulic machines, a cavitation vortex rope that prevent a stable operation due to its instability during a partial load. So when we need to operate at a power demand which is lower than the design point, happening more and more often. Here you can see cracks. All those phenomena lead to cracks and their propagation, their advance, and we cannot forecast today how those advance and when failure will happen. And here you can see erosion, so how particles, sediments, particle collides into, in this case, buckets of Pelton turbines, actually causing unavailability because power owners doesn't want to take the risk to operate, as we don't know how this affects machine lifetime. At EPFL, we have 4 research groups that perform research in hydropower, 2 labs and 2 technology platforms, one of which I'm part of. And here you can see one of a test rig where since almost 60 years, we perform worldwide excellence research in hydraulic machinery. So this is one of the 3 test rigs we are equipped with, where we perform radio-scale model testing of hydraulic machinery on any types that can be applicable to any types of hydropower station. Radio-scale model test means that we are studying a fully homologous turbine, just at radio scale, whose results, thanks to dedicated scaling law, are applicable from a kilowatt scale up to 100 of megawatt scale in a real power station. Here in the coming slides, I want just to show you a few results that we have been recently achieving about how to predict fatigue. And in particular, as I mentioned, being transient operation and startup more and more frequent, we want to know how to predict and how to optimize those trajectories or startup sequence of hydraulic machines. Of course, having such a facility, we want to leverage it. And so we use it with an onboard runner coupled with pressure and strain gauges in order to be able to have a quantitative assessment of this fatigue of the blades. When I was saying that's damage, that's what the damage means. So here you can see the evolution of stresses. I'm going to be a little bit academic, but just giving you the main, let's say, insights of it. So here you have evolution of stresses on an hydraulic machinery during startup. Overall, by using standard stress life methods, this means that we have, during a single startup, an equipment which normally lasts few minutes on power plant, so few decades of seconds in our laboratory. It means that we are an equivalent of 119, so 120 hours equivalent of operation of best efficiency point, one single startup. Thanks to a recent PhD thesis in our lab, we could demonstrate that thanks to variable speed, which is more and more used in power plants, we can actually substantially decrease that. And a simple linear acceleration, avoiding so the synchronization phase thanks to the power electronics, would allow to reduce to almost 15 times, so to a little more than 4 equivalent hours of best efficiency point operation. Yet during those brainstorming studies in which we wanted to quantify the fatigue, so we want to give a perspective to plant owners about how much lifetime they are losing if they perform many startup and stop per day. Yet you can see here quite an important oscillations and alternate stresses, which are particularly harmful for hydraulic machines, but we did not observe there. Why? So we want to dig more. So we are equipped with advanced measurement techniques in order to understand what happens. And I'm proud to say that our result could deliver for the first time in the world, actually, a full characterization of a full flow field in the machine during a fast transient, so during a fast startup. That's because our test rig was the first one to be able to perform a 8-second startup sequence, which will be applicable to variable speed pump storage power station. So our study could elucidate what caused this increase of stresses, a collapse basically of a beautiful cavitation vortex rope that has quite different topology when it goes into transient behavior. And so this allows us to ask ourselves, can we avoid this? And can we optimize a trajectory that avoid all those possible instabilities of a flow? So what I'm showing here is a follow-up project that we had in collaboration with the Swiss Data Science Center, where we wanted actually to showcase that it's possible to not only reduce, but it's also possible to optimize and minimize the damage of turbines. So here you can see that thanks to this study, we could achieve a 5 times reduction of fatigue, thanks, of course, to the use of machine learning methods, so going towards the digitalization of hydropower. These were not just scientific outcomes. We implemented this in real power station. Here it's the implementation of a similar startup that we studied and tailor-made for the application in a power plant, which is really close to Zermatt. You might have heard yesterday the presentation from Canton Valley about the beautiful peak of mountains that's very close to this mountain. And here we could demonstrate that our approach is correct. Our approach is fully transferable to industry. And we can achieve so by putting all constraint in the real power station, a 10 times saving of damage during the startup. Similarly, in a Portuguese power plant, we could extend, so this time not in transient, but when we want to stretch the operating range, we could actually achieve a 100% continuous power variation without having limitation due to this phenomenon by understanding how they impact on operation. So those are a couple of examples. This second one is in Portugal to showcase that test in the laboratory environment, which is controlled, that allow to advance science, can be also be fully transposed to achieve a full transfer of knowledge to industry. So I would like to conclude my presentation by giving few take-home messages. So hydropower is a cornerstone for energy transition. Why? Because we need flexibility, and hydropower is actually a cornerstone of that. We are facing climate change and flexibility requirements that are impacting on hydraulic machinery lifetime, or more broadly on hydropower plant safety. And so scientific activities that EPFL is tackling are key in order to advance the sustainability of this technology. Thank you very much for your attention.